In this final video for the linear algebra part of Math 7, we're going to look at the idea of an isomorphism. So to motivate that, let's think about two vector spaces. The first one is R cubed, the space of all height 3 column vectors with real entries, and the second is M1 by 3 of R, which is the space of all width 3 row vectors with real number entries. So a typical element of this one looks like this, where x, y, z are real numbers, and a typical element of this one looks like this. It's a row vector of width 3 containing 3 real numbers x, y, and z. And these are in some sense the same as vector spaces. They have exactly the same properties in terms just of vector spaces. But they're not equal as vector spaces, because one of them consists of row vectors and the other consists of column vectors. So how can we make precise this idea that these are not the same as vector spaces, but they share all possible properties which could be expressed just using the language of vector spaces? The answer is in the concept of an isomorphism. Here's the definition of an isomorphism. A linear map which is also a bijection is called an isomorphism, or sometimes a vector space isomorphism. And there's some notation for when there exists a bijection between two vector spaces. We write U and then this equals sign with a wavy line on top, and then V and we say that U is isomorphic to V if and only if there exists an isomorphism from U to V. So as an example of this, let's take those two vector spaces that I was talking about on the last slide. So example, we'll take the map F from R cubed to a set of 1 by 3 row vectors with real number entries, defined by F of the column vector x, y, z is equal to the row vector x, y, z. Now it's very easy to show that this is a linear map and that it is a bijection. It's one-to-one and it is onto. It follows that these two vector spaces are in fact isomorphic. And we write R cubed and then this symbol and then M1 by 3 of R. Okay. So one of the nice properties of isomorphism is that it gives you what's called a symmetric relation on vector spaces. That means if U is isomorphic to V, then also V is isomorphic to U. So in some sense, the notion of isomorphism shares some of the properties of the notion of equality. Certainly if A equals B, then B equals A, no matter what things A and B are. And similarly, if U is isomorphic to V, then V is isomorphic to U. We're going to prove this on this slide by proving this lemma, which says that if T is an isomorphism from a vector space U to a vector space V, then T inverse is also an isomorphism from V to U. Let's think how the proof should go. So to do the proof, well, we know that T as an isomorphism is a linear map which is a bijection. So linear bijection. So what we have to do is to prove that T inverse, going from V to U, is also a linear bijection. But we know that the inverse of a bijection is, again, a bijection. So that part comes for free. The inverse of an invertible map is itself invertible. So T inverse is a bijection. We just have to show that it's linear. So this is a result I actually used a few videos ago and told you I was going to prove it later. Well, here I am keeping my promise. So we want to show that T is linear. So let's pick two things in V, two vectors in V, and show that T inverse of their sum is the sum of T inverse applied to each of them. So the additivity property, part of the definition of linearity. So we'll let X and Y be elements of V. We need to show that T inverse of X plus Y is T inverse of X plus T inverse of Y. So we're going to do this using the fact that T is a bijection, so T is onto, and that means X and Y are both equal to T of something. So let's say X is T of U and Y is T of V for some vectors U and V in U. Now let's look at T inverse of X plus Y. So what's that? That's T inverse of T of U plus T of V. Now T we know is a linear map. That's the assumption in this lemma. T is an isomorphism, so in particular it's linear. So T of U plus T of V is the same as T of U plus V. Okay, but now we've got T inverse of T of something, and T inverse composed with T is the identity. So this is just U plus V. But if you look at this thing here, for example, what does that tell you? If you do T inverse to both sides, you get that U is T inverse of X. And similarly, V is T inverse of Y. So what I've got here is T inverse of X plus T inverse of Y. We've shown that T inverse has the additive property. Now we have to show that it has the scalar multiples property, that T inverse of A times X is equal to A times T inverse of X for any X in V and for any scalar A. I'm not going to do this. You should have a go at doing it. If you can't solve it yourself, or if you want to check your answer, you can look in the online notes for Math 7 and you'll find a proof there. Okay, so the inverse of an isomorphism is also an isomorphism, and the point of doing this was it tells us that if U is isomorphic to V, then V is isomorphic to U. So this is a symmetric relation, that's the technical term. Okay, let's see some properties which isomorphic vector spaces must have in common. And one of them is that if U is isomorphic to V, then the dimension of U is equal to the dimension of V. So the general principle here is that if two vector spaces are isomorphic, then they should have exactly the same properties as vector spaces. So any property that you can state just using the language of vector spaces, not referring to the specific form of the elements, but just talking about these vector spaces as vector spaces, should be shared by any two isomorphic vector spaces. And an example of such a property is the dimension. So this result says that if U and V are isomorphic, then they have the same dimension. And we can prove this with the help of the rank nullity theorem and the existence of an isomorphism from U to V. If T from U to V is an isomorphism, then by the rank nullity theorem, the dimension of the kernel of T plus the dimension of the image of T is equal to the dimension of the domain of T, which is U. Now T is a bijection. An isomorphism is a linear bijection, so T is in particular a bijection. And so, since it's a bijection, it's also onto, which means the image of T is all of V. So the dimension of the image of T there is just the dimension of V. And also, because T is 1 to 1, the kernel of T is the 0 vector. We've actually proved this before on a previous slide. The reason that it's true is that we know T of the 0 vector in U is equal to the T of the 0 vector in V. So because T is 1 to 1, T can't map anything else to the 0 vector in V. So the kernel of T is just the 0 vector in U, and its dimension is therefore 0. So plugging into the rank nullity theorem, what it will tell us is the dimension of the kernel of T, which is 0, plus the dimension of the image of T, which we just established is the dimension of V, is equal to the dimension of U. And so we get the dimension of V and the dimension of U are equal as claimed. Now, in fact, the converse is true as long as you restrict to talking about vector spaces over the same field. So any two vector spaces of the same dimension over the same field are isomorphic. That's what I mean by sort of. I mean, you have to have this extra qualification that you need vector spaces over the same field. Remember that we only define linear maps between vector spaces over the same field, so there can't possibly be an isomorphism between two vector spaces over different fields. Okay, so in order to see that that converse which I mentioned is true, we're going to prove this, this final result in our linear algebra section, which says that any f vector space of dimension n is isomorphic to the vector space of all column vectors of height n with entries from f. And as usual, f just refers to either the real numbers or the complex numbers. So I think this is a kind of disappointing result. Certainly when I first heard this as an undergraduate in my linear algebra lecture, I was extremely disappointed by this, because it means vector spaces are really just kind of boring things. Finite dimensional vector spaces, at least, are kind of boring, because every single one is basically the same as some column space. And column spaces, well, they're just column spaces. So for me, this was a bit of a disappointment, a bit of a downer to end this section on, but we're going to do it anyway. So we take V to be this vector space with dimension n, and our claim is that V is isomorphic to f to the n. I'm going to give a sketch proof of this where I don't check some of the details, but if you want to see those details again, you can look them up in the Math 7 online notes. So the dimension of V is n, so it has a basis of size n, and we'll pick such a basis and call it V1 up to Vn. We then define a function t from V to f to the n in the following way. We observe that every element of the vector space capital V can be written uniquely as a linear combination of V1 up to Vn. That's a property of bases we introduced and proved quite a while back in our first lecture on bases. So I can define my linear map T by saying what it does to a linear combination of V1 up to Vn, since every element of V can be written uniquely in that form. And I just define T of a linear combination I equals 1 up to n ai vi to be the column vector whose entries are a1 down to an. So in other words, what T does to a vector in V is just send it to its coordinates with respect to the basis V1 up to Vn. Now this is a linear map. You need to check this, but it's not very hard to check. It is 1 to 1. I think it's kind of clear that it's 1 to 1, because if you have two things with the same image, then they are both equal to that the first element of the image times V1 plus the second entry of the image times V2, and so on. So 1 to 1, this is very easy. Onto is very easy, because if you have any column vector a1 down to an, well, that is the image of the linear combination a1 v1 plus a2 v2, and so on, and therefore it's a bijection. So we're done. We've proved that every single finite dimensional vector space is isomorphic to a space of height n column vectors.